So I'll talk about what extensible type state is, and I'll mention a little bit about extensible effects to the minimum possible, minimum that needed to understand the talk. But if you want to have more details, that on Thursday there would be Thursday morning there would be a tutorial about extensible effects, and then there would be more talk and more explanations. What's interesting, or kind of the cute part of all the things, is that if you look at the inferred type state types of the computation, that they look like session types, which is quite surprising. Well, actually kind of expected, but you know, they actually look quite like session types, which was, I mean, interesting thing, so at least cute. Okay, so about type state. Type state was introduced by Strom and his co-authors back in the last century. And you can see it was, the first paper is on 1986, so it has been 30 years past. And this usually about the right time for ideas for computer science to beginning to get into practice. So I heard that type state was considered for Rust, and then they dropped it. So I hope that maybe, I mean, this new kind of, I mean, take on the effect, maybe, I mean, make them much more, a little bit easier to deal with. So here is that first example of the type state. So we know the type of the value determines whichever operations they can be performed on. For example, if the type is, I would use for first type, first part kind of OCaml-like syntax. So if we know that the type is in channel, then the possible operations that can be applied to is like read input line and close in and so forth, so forth. We cannot apply it successively. But if you look carefully into that code, then, or actually an operation, that we know that input line actually applies before we close the file, but doesn't actually apply after we close the file. So it means the set of operations depends not only on the type of the value, but also on the program state. And that's what the type state is all about. And here's maybe a more familiar example with a client release log. For example, the operation release is applicable only after log has been acquired, only in this program state. But here are the example that we will talk about, we use in this talk, is the initialization problem. And actually, this is the example that prompted the introduction of the type state. And it's also the same example that uses a motivation for the language meso. So if we have, we want to create a variable or reference cell and initialize it from some value that we read from the file. So that's very easy to do. But suppose we want to have two variables, two reference cell initialized to some values which read from the file. But it's not just we read from the file. So we read something from the file and we perform the computation, and then we wanted to bind it to values x and y's. Well, of course, we do something like that, but the problem is, well, as in red. So we have to construct the pair or tuple, and then we have to perform deconstructing the tuple. So that's kind of annoying thing. So constructing and deconstructing the things. Of course, one of the ways to kind of make it more elegant is, well, first initialize with some kind of dummy value and then override it. Well, it's a mutable cell. And that's actually how often done in C, for example, right? But, I mean, if we look at that, yeah, in some cases, it's kind of, I mean, nicer, but on the other hand, it's actually much worse than before, right? Because, first of all, we have something like dynamic typing. For example, at this point, we can try to perform some operations on x and y's, but they have nothing. So, therefore, it would be dynamic error. And moreover, at this point, we stuck permanently with doing from sum. So we have permanently stuck with this doing projection. So it's actually much worse than before. So the ideal solution would be something like that. So we first initialize with, for example, unit. So if we try to use it x and y's right away, then it should be a type error. But after we initialize it to some kind of integer, then this code should be okay. And in fact, this is kind of, I mean, modules some stylistic differences as how you can write in meso. And what we end up with, I mean, time permitting, is we'll write this in Haskell. Roughly the same code with some different syntax. Okay, now about the second part about extensible effect that we are going to generalize. So we start with a almost normal monad state, but instead of having one piece of state, it has, well, several pieces of state that with a statically known names which name var. So you can think about a statically known reference cell, statically known variables. And I mean, given this particular class, we can write computation. For example, this computation gets something from the variable, puts character into that, and returns that next character after that. And its inferred type, which is it's inferred, is that M should be some kind of monad that satisfies this constraint, such that assigns to variable 1 type character. And this is a very similar computation, well, that deals with var2 and deals with integers. And the nice thing, we can use both of this TS1 and TS2 in the same computation. And this is the type which inferred for it. So it's a very nice type, right? So it can have, I mean, variable 1 has to be character, and variable 2 has to be integers. And of course, we can write it, and it's all nice. But I mean, in order to write for that, it says, well, there exists an M that satisfies this constraint. But in order to write for it, we actually have to have that M that satisfies this constraint. And let's make the one that, I mean, one M that will satisfy this constraint. So this is a free monad. So it looks like a free monad, but as you can see, it is a monad, well, for any F. So F doesn't have to be a functor. And in fact, in our examples, it won't be. So the meaning of F is effect signature. So it tells what kind of effect is going to perform. And because we're interested in the state effects, this is the signature which we saw state var S, that would be our F. So the effect would be modified a variable. So I also would, instead of, well, usually when we think about state, we think about get and put. And here, for explanation and for the contrast, I use single operation modify, which obviously you can express get and put through this operation modify. But if you're interested in get and put, that you can also do. And of course, now we can write an interpreter for that given this computation of state, runs this computation and returns accumulated state and so forth. So I won't write this interpreter. The most interesting thing is, well, relevant for us is that this F, the state monad, does satisfy the monad M state constraint. And this is the proof that it does satisfy. So whenever it simply sends this message modify tr, and this interpreter would handle this message. And we can run TS1 computation because we can assign TS1 this type that says it's a factful computation. And the state signature or effect signature says it's a state computation with variable 1 associated with characters. And then we can run it. And of course, we can run this one as well. TS2, we associate var2 with integers. But of course, here we have the problem. I mean, what should be the state signature for computation that satisfies both of the constraints? Well, we need to have the meaning. We need to have some kind of union. Well, let's make the most trivial union that we can imagine is just a ether type. So left and right. Of course, there are many other better ways of building a unions, and I myself have 5 different ways of using unions, which are much more sophisticated than that. And we just heard, 2 hours ago, talk about row polymorphisms link. We're also concerned about this union. So there are many different ways. But it's irrelevant how you implement the union. So interesting part of it is that this union satisfies the constraint, satisfies monad M state constraint, and a left part, if the left part is a state, then it satisfies constraint, and the right part satisfies constraint. And now we can assign TS3 this particular type. So it's a sum that has var1 associated with character, var2 associated integer, and then we can run this computation by composing to both interpreters. So that's the extensible effect. So we can. But we wanted to have modify not only value, we want to modify the state. So we wanted to write something like that. So we put in the variable C, in the variable 1 character, and then put in the variable 1 boolean. And the GHC, first attempts to infer this type and then complains. And the problem is it infers the type that, well, it has to be monad M state where variable 1 associated with characters and variable 1 associated with booleans. Well, obviously, it cannot be associated with both at the same time, right? So then it complains about it. So what we need to say is that it was affiliated with characters, and then it somehow started with booleans. So we need to have a notion of time or notion of sequencing. Notion of evolution. And there has been a way of how to deal with this. Evolution is a parameterized monad. So it says, looks like kind of like a monad, but we have these two parameters, S and T. So you can read this kind of bind operation like this. So we started computation that produces or promises to produce the value A, and it starts with the computational state S and ends with T. And then after that, we take this value A and starting with T, go to the computation state U. And so this full computation gets from S to U. So, and there is, I mean, the name monadish kind of implies that it's kind of generalization of monad. So, well, that looks kind of a generalization of bind. So the question, why there isn't any generalization for return? No?
SS or something?
That's just normal return for MSS.
Yeah. Well, I mean, yes, but I mean, why? Okay, yes, that's the reason. So we can just as well generalize our F type, adding S1 and S2, and generalize state type, taking S1 and S2. So it means we are going to modify a state from S1 to the state S2. So this is just a straightforward. So we generalize just adding those two state S1 and S2. So it's all straightforward. And this is actually, I mean, what indicated. So it turns out, so if we have S and S, the parameter is the same, that it's a monad. And therefore, we can use return from that monad. So we can kind of use extensible monadish and monad roughly in the same thing, in the same computation. Now, the only thing, well, we need to generalize our monad M state with, I mean, also that it varies the state. And of course, the obvious thing is to say, well, we just add S1 and S2 parameters. Unfortunately, this obvious thing doesn't actually work. Because when we say we wanted to modify variable 1 from, I mean, value in the state from being a character to being a Boolean, that state, computational state, has other variables, right? So it modifies only variable 1 from state to Boolean, but all other things should remain unmodified. And this type doesn't actually says that. So instead of, we need to have this much more complicated thing. It's a sixth-place relationship. And so how to read this? And the nicest way to read it is this way. In the security policy M, according to security policy M, so if the computation, if the policy allows in state T1 access the variable var as S1 and changes to S2, then the computational state changes to T2. So it kind of permission in the state to modify one variable to particular value, and the overall state, of course, changes correspondingly. So how to implement, well, that's union that, how to write the monad that satisfies this constraint? It's actually a very complex question, and I don't even have time to discuss it. So I just show the final result. So we can write this computation. So it has two variables, var1 and var2. So we read the both variables, and in var2 we put character C, and then we put in var1 obviously string. And from this you can see that x and y should be integer or num type. So it changes. It has two variables, and it changes state of both of them. And if you look at the inferred type, the type says that it started with some kind of state t, and in that state t, variable 1 was affiliated with integer. And as you can see, we use the previous, it's not extensible, not parameterized monad state. And in that state t, variable 2 was associated with integers. And then variable 2 changed from integer to characters, and the type advanced from t to t1. And then in var1, type advanced from t1 to u, and var1 became string. So as you can see that, if you look at this type, it now becomes, kind of looks quite like session types, right? So it progresses. We first do that, then we do that, then we do that, and we do that. And this type is inferred, actually. So, well, that's kind of near the end of it. So what can next be about it? What I have, I mean, I know in the code that you can download, there are more examples that of, I mean, similar computations, but other things which are interesting to encode into this framework. First of all, it's interesting to write a type that says first, before any get, there must be a put. So that's one of the interesting type. Another interesting type that could be written in this framework is that so put and get alternate. So we have put, get, and after that it must be a put after get. So that's another thing. And it's also an interesting question to ask if standard non-parameterized f, it kind of corresponds to delimited control with answer type modification. So what should be the continuation dual of FT? So I have no idea. So, well, this is the end of the talk, and this back to the summary. So yes, I mean, I talked about extensible type state, which is a generalization of extensible effects with some non-trivial twists. And if we look at the info type, then it indeed looks like a session type. Okay, thank you.
Questions?
Yes.
What's actually the current state of session types? What is the current state of session types? Are there good libraries? I looked like a year ago or something. Well, Haskell, for example.
Lots of libraries.
Oh, okay.
Yes.
Yes. The Haskell symposium about embedding session types.
Yes. So there is, I mean, continuously, I mean, improving. Yes, and there is. Yes. Simon.
So in your example, you had these kind of two fixed variables, var1 and var2.
Yes.
And you were sort of indexing them by types, which presumably, so it's a bit like manipulating global variables. But when we're doing state transformers, we're often saying, you know, x is new f, and we're making up new variables all the time.
Okay. Yes. No. Well, I mean, I know.
Was that just for the example, or does making up fresh variables make what you're describing more difficult?
Would make it more difficult. I mean, because, well, this is one, the variable, the names of the variable known statically, right? So
that's what I mean.
Yes.
But if the names are not known statically.
Yes, well, I mean, so the type of the state is, I mean, it's not, well, it's possible to create them dynamically, but then, I mean, if you create it dynamically, the type becomes higher rank type, right? And therefore, I cannot make any inferred types. Yeah. Well, here, everything was inferred, right? So, I mean, the type system is, I mean, so if I try to make it random, so I have to do quantification, right? And then I have to write signatures.
But real programs are going to need.
Yeah, well, yes, I mean, so. Well, now maybe it would be easier. Now in GHC has this underscore, so I mean, I know. So I did it before this underscore appears. So I mean, that writing all the constraint would be a little bit too cumbersome. Oh, Adam.
Yeah. Did you consider with these variables to have just a sigma type consisting of a type and an element in it? And if it's too large, you can replace it by a universe.
Well, I mean, I know. But in this case, I mean, I know the meaning of var, right? So it determines it's kind of, I mean, var is just a name. There is no, I mean, no type associated with var, right? It depends on what you, I mean, what the program. So when I said about security policy, I wasn't actually kidding about it. So you write the code, like you say, put some value of some type in the variable var and puts another type of variable var. And so then I execute this program into this interpreter, and the interpreter determines what the security policy is. So one of the interpreters says, I'll allow you to change var1 from integer to boolean. And another interpreter says, I don't allow you to change integer to boolean, only integer to characters. So I don't want to fix, I mean, what my meaning of variables should be. I wanted to be able to decide later on. Yes. Okay.
So when you have these operations that have these monadish types, right? You have write, and it goes from state A to state B.
Yes.
If you collect those in a kind of clever way, the state transitions define as DFA.
Yeah.
Right? And then you could use a regular expression, right?
Yeah.
Policy over what's
yes,
right?
yes, that's correct. Yes. So essentially, yes, yeah. So if you come to more complicated session types where you need to have a mu and recursion, that's exactly regular expression would be. Yes, you're right. Exactly.
So that might be one way of.
Yeah. You're exactly right.
Maybe one more question while the next speaker comes up.
Okay,
So in the type you gave,
yes.
As you point out, it's like a session type in which all the internal machinations of the function are exposed.
Yeah.
But when I use one of these functions, I don't really care how it works inside. I just want to know what state I must provide it, what variables must be in the state and what types they have, and what state it's going to produce. I'm not really interested in the stuff inside.
Well,
You have to throw that at me.
well, the reason how I interpreted the security policy, I said that the handler would either permit you to, so you asking the handler, am I allowed to change this variable from integer to boolean? So you do not expose all the machinations, you expose all the modification of the type state. And the M, which would say, well, I would allow you this modification, or I would not allow this. So that's how I prefer looking at this.
Okay, let's thank Oleg again.